Assalamualaikum warahmatullahi wabarakatuh. So welcome to our class. So today we will continue with chapter number 2 on the theory of operation of real single phase transformer. So basically this is the outlines of the practical transformer that differ from ideal transformer in several ways. So first of all, we do have we consider the as resistance of the windings. Okay, so we represent it as R. Then we have the flux leakage between the windings that lead to inductive reactance effects. So the reactance X, for example. Okay. And then the magnetizing current is not zero, but it may as little as 3% of the load current. So this is what we consider with the magnetizing current. The amount is about 3% of the load current. And then there is power loss in the iron core due to hysteresis and eddy current effect. So we name it as H plus E, or the core. All right, so this is the core loss. Right. So due to the hysteresis and eddy current effects. And then the last part is the capacitive effects are present in high voltage transformers, affecting the ability to withstand strikes of lightning. So since the capacitive effects consist of high positive and negative charge, and due to that, the ability of transformer in order to withstand from lightning is very, very weak. Okay, in the sense that the transformer is now having the lowest point of withstanding from the lightning strike. So then if you look at this diagram, so the mutual flux over here, okay, here, okay, leakage flux, sorry, and here again the leakage flux. So we have both sides, especially the primary and also the secondary. So here this is the mutual flux that flow inside the core, particularly this rectangular core, moving from primary to secondary and back to the beginning point to complete one cycle, and this is known as mutual flux, the phi m. So what about the leakage flux? So we have again at both sides here flux Ls, leakage flux at secondary, as well as the leakage flux as at primary. Okay, and then the total flux X at primary phi p, this is actually equal to phi m plus phi lp. Okay, the leakage flux at primary as well as the mutual. Okay. So similarly, if you go to the secondary side, so you may see the average flux as the secondary flux equal to flux m plus flux L ls. Right? So again, this is the total average secondary flux. So now, according to Faraday's law, so the basic transformer operation can be derived from E induced equal to d lambda over dt over here. Okay, where lambda here, okay, this is nothing but flux linkage in the coil across which the voltage is being induced. Okay, so it's somewhere in between here, right? Here and here. Okay, so it happens or it occurs in between the flux linkage across the coil, of course, which the voltage is being induced, and then some of the flux passing through each turn in coil. And then average here is again the average flux per turn. So this is equal to lambda over n, and just rearrange. Okay. Now we have here into the first equation giving us the final E induced equal to N the average flux d phi bar over d dt. So N is of course the number of turn. Okay. So yes, this is some of the definition of what I have explained earlier. So motor flux is flux which remains in the core and links both windings. Meanwhile, leakage flux is flux which passes through the primary winding but returns through the air by passing the secondary winding. And then for the secondary winding, the leakage flux is the flux which passes the secondary winding but returns through the air by passing the secondary windings. And then from the diagram, so we are able to re-express Faraday's law. So how it works, so this is the induced voltage at primary, the induced voltage leakage at primary, of course, due to the leakage flux, as well as the induced voltage at the secondary and due to the leakage flux at the secondary. And yes, here we go due to mutual flux, and this is the equation. So we have Vp and P d phi average over, or d phi bar over dt. So we derive this again because in the phi P consists of mutual flux plus M as well as the phi Lp, the leakage flux. Okay. Same goes to the secondary part. We have the Vs equal to Ns d phi bar over the dt. So ds or the phi s actually consists of phi n plus phi ls, the leakage flux. The primary and secondary voltage of the mutual flux is given as Ep and Es Np d phi m. This is what we have seen in the previous page. And the relationship between this equation is Ep. So this is after we rearrange from this main equation. Okay, so just rearrange into Ep over Np. This is equal to d phi m over dt, and this is actually E Ts over Ens. And again, from here you may rearrange the equation in order to obtain A, the turn ratio. So this is again nothing but Ep, okay, over Es or Np over Ns in terms of number of turn as well as the voltage Vp over Vs. And then some of the consideration also. So the current flows in primary circuits consist of magnetization current, namely Im, to produce flux in the transformer core. Okay, and then the second element is the core loss current. So this is what I have mentioned in previous slide. This is due to hysteresis and also eddy current effect to make up for hysteresis and eddy current losses. So these two are known as excitation currents, or Ix equal to Im plus IH plus E. So the average flux in the core is phi bar equal to 1 over Np. So just integrate Vp respect to times over dt. So if Vp equal to Vm cos omega t, so just substitute into here and giving us the final equation of average flux of phi bar is Vm over omega Np sine omega t, and this is the unit Weber. Okay. Okay, the current flow into dotted line over here. So this is what it means by this symbol, the red dotted N. Okay. And then currents flows into undotted end, this part representing here, and this represent here. Okay, as well as this symbol and this symbol. Okay, this means we have two sides of transformer where current flows into dotted line and current flow into undotted line. Okay. And then from here, okay, so the net MMF, the magnetomotive force, okay, in the core, F net equal to NPIP minus NSIS equal to flux R. So the reactance over here is nearly zero because due to well-designed transformer. Okay. So the losses to be considered in any accurate model of transformer. So we have first the copper or I square R losses. Mainly the resistive heating losses in the primary and secondary windings. We could say this is actually R losses. Okay. And then the second one is eddy current losses. This is the resistive heating losses in the core due to the complex or nonlinear function of the voltage applied to the transformer. Similarly, goes to the hysteresis losses associated with the rearrangement of the magnetic domains in core. And again, these two are known as core losses. ELOSSES. Okay. And then finally, the leakage flux, for flux from LP and also flux from LS that escape the core, or we can simply write it or represent it as the X losses. Okay, the reactance losses. So equivalent circuit of a real transformer. Alright, so we have first the leakage flux. So this is how we write or we represent in the equivalent circuit. So we have JXP, so we have JXS as well. Okay, and then the second part we have copper losses here. Alright, the second one, so this is first and this is second. So the copper losses represented by RP and RS. Again, since we have both sides, primary and secondary, suppose we have RP as well as RS for the copper losses. And then the final losses is the core loss current IH plus E. So this is the excitation branch over here. So we have JSM plus RC, or also known as or due to the core loss current. So what about the transformer model referred to primary voltage level? So this is how it looks like. So we have simplified the previous equivalent circuit into this simplified circuit when the transformer is transferred to primary voltage level. Okay, so let us go back to the previous or the full complete circuit or the equivalent circuits where we have the again the primary and so the secondary. So we have the excitation branch over here. Once we come to we simplify the model, we do not have this part any longer. All right, the turn ratio, the winding is no more exists, and we just have the primary as impedance as well as the secondary impedance and this branch. Okay, so once we refer to primary, so now we have the E square RS as well as A square XS. And what happened to I? So I we just divide by A, and Vs we multiply by A. So we have shift or we have moved all the element in secondary. Again, I repeat, I, V, RS, and XS over the A and settle down in primary. Okay, just imagine this is your A with the coil over here. Okay, so now we have shift or move over to primary, and we have changed the element of IS, VS, RS, and XS, and it is now come in series. All right, so here now it come in series, everything. So everything in series. This part and this part, the one I color in, let's say yellow. All right, so this is in series. And what happened to this branch? So we just simply move to the beginning of the model or beginning of the circuit over here. Okay, so we just again move to the beginning of the circuit due to, all right, very small current that happened that the here. Okay, again change the color. So here very small current compared to the load current causes completely negligible voltage drop in RP and also X. So the excitation branch is simply moved to the front of the transformer here. Okay, the one I color in purple is simply moved to the front of the transformer, and the primary and secondary left in series with each other. This means here and here left in series, just like this diagram. Okay, so they are all connected in series, and R equal P equal to RP plus A square RS, X equal P equal to X equivalent P equal to XP plus A square X XS. Okay. Similarly, if your transformer model refer to secondary voltage, now we have the new RP, which is now RP over A squared, the new XP, which is now XP over A squared, the new IP, AIP, and new VP, which is VP over A. Right? So this means everything, let's say we have the winding over here with A number of turn, right? So we have our impedance of RP here, and we have XP, and now everything here, including the IP and VP, have been here all shifted here and or jump over to the secondary side, crossing A. This means you need to multiply A squared RP, A squared XP, and A multiply or times IP, and VP over A. And by doing that, you are actually eliminating this part. Okay, the winding part is no longer exists, and everything here again are connected in series. Okay, between again this primary and this S and S secondary means RS and XS. That's why we can simply come out with equivalent R as well as equivalent X, and they are all connected in series. RP over A squared plus RS, XP over A squared plus XS. Okay, so S, IS, VS, RS again, and XS remain unchanged. So determining the values of component in the transformer model using open circuit test and short circuit test. There are actually two methods we can use in order, okay, to determine the values on component. For example, the REQ, the XEQ, as well as the RC and also XSM. So we will see in much better when we come to the exercise. However, we try to understand how the method works. So the open circuit test, for example, so this is nothing but secondary winding is open circuit and primary winding connected to full rated voltage. Okay, and then what is short circuit test? This is actually a secondary winding is short circuit and primary winding connected to low voltage source. The voltage is adjusted until the current in the short circuit winding is equal to its rated value, but you have to be extra careful because you may burn out the transformer winding, right? So this is two methods on how we can determine or obtain the transformer components value. Open circuit test. So this is the diagram. So we have VT over here. So we have the voltmeter to measure the voltage. So we have the ammeter to again measure the current, and then the wattmeter to measure the P, the watt, and it is open circuit at the load side of or the secondary side. Okay. The total excitation admittance. So what is admittance? So this is actually how easy a circuit or how easily a circuit or device will allow a current. This means how easy the current to flow inside the circuits. So, and then we have YE equal to, yes, the admittance, Y, E equal to GC minus JBM. So what GC is a conductance. Here is conductance of core loss resistor. Okay. How about the BM? This is the subsistence of magnetizing inductor. Again, so the subsistence over here is actually imaginary part of admittance. All right. So again, admittance, if we can write in simple form, this is actually 1 over Z. Okay. The inversion of Z. And then the easiest way to calculate RC and RM over here, all right. The easiest way to calculate RC and SM is to look first at the admittance here of the excitation branch. Okay. And then the conductance of the core loss resistor is given by GC equal to 1 over RC. Okay. And then finally, subsistence of the magnetizing inductor is given by here. So we have done with GC. So we have BM over here. Okay, the substance equal to 1 over X SM. Okay. So this is how the easiest method you can use in order to calculate the excitation admittance. So the magnitude of the excitation admittance again referred to primary circuit. So we have modulus YE. So this is equal to OIOC over VOC. OC means open circuit. Again, the open circuit power factor PF equal to cos theta equal to POC open circuit over VOCI OC, and then the admittance YE with its angle. So YE equal to IOC VOC. So minus theta due to the lagging where angle of current, okay, angle of current always lags the angle of voltage. Okay. So this is the reason why we have negative power factor or a negative theta arc cos power factor. Okay. And again, we use this YE in order to obtain the value of RC plus XM that occurs in core loss. What about the short circuit test? So meanwhile, short circuit test, again, we do have something like similar to what we have just now, the diagram or the equivalent circuit of the transformer, unless for the ending part here or the end part over here is now being short or connected. All right. So since VT is low voltage, current flowing into excitation branch is negligible. Series impedance referred to primary. So we have the modulus ZSE, the series Z equal to VSC. SC stand for short circuit over I short circuit. So this is again the magnitude of series impedance. So next, the power factor of the current. So the equations is very straightforward. We have PF equal to cos theta equal to PSC, again short circuit over VSC times ISC. Okay. And then overall impedance, we have ZSE, VSC over ISC. So VSC over ISC with theta. Okay, again, so this is a negative due to the current angle is lagging the voltage current. Okay, and then the series impedance is actually the copper losses. Okay, this is actually, let me write for you, this is actually, oops, double P copper loss. All right, and then being referred to primary side. Okay, we have ZSE equal to REQ plus JXEQ. ZSE is actually RP plus A square RS and JXP plus A square RS. So nothing happened to the RP, so still remain the same. XP also, this means the transformer is currently referred to primary. And in general, the short circuit method or technique over here is actually to find the value of REQ and also XEQ. All right. So example number 2, the equivalent circuit impedance of 20 kVA, 10 kilo down to 240 volt, 50 hertz transformer are to be determined. So the open circuit test and the short circuit test were performed on the primary side of the transformer. So the primary side of the transformer, and the following data were taken. So find the impedance of the approximate equivalent circuit, refer to primary side and sketch that circuit. So it has been clearly stated that the transformer is currently referred to a primary side. So you have to calculate according to the data given over here, open circuit as well as short circuit, the VOC, VSC, IOC, ISC, POC, and also PSCD, P power. So let me go to the slide of example to answer. Okay. So the power factor during the open circuit, okay, just refer to the previous equation. We have power factor cos theta POC over VOC IOC. So use or utilize the equation and substitute all the given value in the question. So you may get the power factor is 0.234 lagging. So the lagging have been justified in the previous slide. And then the excitation admittance is given by, remember this is Y E IOC over VOC minus cos theta. Again, the negative is due to the lagging condition. And then up cos 0.34 to get the value of the angle, and IOC VOC again. So just substitute from question. So giving us the value of I1 over RC minus J1 over SM is actually 0.000063 minus J 0.0000261. Okay, so invert it in order to get the value of RC and SM. So giving RC 159 kilo ohm and SM equal to 38.4 kilo ohm. So how about the short circuit test? So again, okay, sorry, from here we may know that for the open circuit test, we are able to find or to figure out the value of RC and SM. And then for short circuit test, we have cos theta PSC over VSC ISC. So again, substitute all the value provided in the question, especially the table. So 240 for the watt, for the V as well the I. So 0.196 lagging. So the series impedance given by Z VSC over ISC cos power factor. So cos this value and giving us 78.7 degree. And this is nothing but from the table or from the question. So finally, the series impedance equal to 38.4 plus J192 ohm. And from here, we can simply figure out the value of REQ, right, as well as the XEQ. Or therefore, the equivalent resistance reactance are here, right? I say, okay, this is the end of this particular part, and I hope we can still continue with the next episode. So see you again. Have a nice day.